Welcome to Draw the Logic, where we make complex ideas visual. Ask two different tools the exact same question. One gives you 10 links in under a second. The other one just sits there, thinking, for minutes. So what is it actually doing in there? That's what this video is going to open up. A search engine is a librarian. You ask a question, it points you to a shelf, and you do the reading. Deep research does something else entirely. It reads everything itself, keeps what matters, and quietly sets aside what doesn't. Then it hands you the memo it would have taken you all afternoon to write. Here's the kind of question that breaks a normal search box. It's not one lookup. It's three, chained together, where you need the answer to the first before you can even ask the second. Deep research doesn't just search once and hope. It works the chain, one link at a time, and only then commits to an answer. Before any of that is possible, the model has to go through something much simpler first. It just reads trillions of words, web pages, books, code, poured into a network whose only job, at this stage, is to guess what word comes next. Here's the part people get wrong. The model doesn't know Paris is the capital of France the way a database knows it. It's ranking every possible next word by probability, and Paris just wins by a landslide. It picks the highest scoring guess and moves on. Now repeat that, one word at a time, across every sentence it's ever trained on, and across every sentence it will ever write. That single mechanic is the entire engine underneath. The next word trick alone got dramatically better with scale. In 2018, the first version had 117 million adjustable settings, a rounding error by today's standards. 2 years later, that number passed 175 billion. But the leap that actually matters for research isn't just size, it's memory. Newer models can hold 1 million tokens at once, entire reports, entire code bases, and view all at the same time. A model can answer instantly, the same way you can blurt out a gut reaction, and sometimes that gut reaction is wrong. The best research models have learned to pause and show their work first, checking their own steps before committing to an answer. That habit, thinking before answering, is what separates a chatbot from a researcher. Straight out of training, a model isn't polite, careful, or even reliably honest. It's just very good at finishing sentences. So it goes through a second stage. One approach has humans grade its answers, thumbs up or down, until it learns what good looks like. Another approach, the one Anthropic uses for Claude, skips most of the human grading and instead has the model critique its own answers against a written set of principles, over and over, until it converges on the same result. Different roads, same destination, a model that's actually safe to hand a real task to. Every one of these systems, OpenAI's, Google's, Anthropic's, runs some version of the same three-stage loop. Plan the approach, go gather the evidence, then synthesize it into something coherent. We're going to walk through each stage, one at a time. The first move isn't searching. It's breaking the question apart into the smaller questions that actually need answering. And critically, this plan isn't hidden. You can see it, and in most of these systems, you can step in and redirect it before a single search happens. To actually go get evidence, the model reaches for tools. A browser to read live web pages, highlighting the signal, ignoring the noise. A code sandbox, so it can run real calculations instead of guessing at math. And when it's connected to private company data, it's typically locked to read-only. It can look, but it can't change anything. Now it has a pile of evidence, and that evidence doesn't always agree with itself. Instead of quietly picking a side, a well-built system flags the contradiction. Then it compresses everything down into a structured report, where every sentence you read traces back to something it actually found. There are two very different ways to build this. OpenAI's approach keeps one central model holding the entire picture in its head at once. Anthropic's Claude does something different. It splits the work across a team of smaller agents, each holding only its own small slice. One capable model acts as the orchestrator and hands off each subtopic to a team of faster, cheaper worker models running in parallel. Any one of those workers can decide its slice is still too big and spin up its own helpers underneath it. Once everyone's done, The findings flow back up to the orchestrator, who's the only one that has to write the final answer. Say there's roughly a 1 in 5 chance any single agent gets a specific claim wrong. Now have a second, independent agent check the same claim from a different source. For the error to survive, both have to be wrong the same way, and that's a much smaller chance. Add a third and a fourth independent check, and the odds of everyone agreeing on the same mistake don't just shrink, they collapse. 1 in 5, down to 1 in 600. This isn't a hunch. It's the actual mechanism behind why Anthropic's multi-agent setup so dramatically outperformed a single model working alone. If every step has to finish before the next one starts, one slow or broken website can jam the entire process. Google's engineering answer for Gemini was to make the whole thing asynchronous. Tasks run in parallel, and if one fails, it gets isolated and retried without taking anything else down with it. That's also why you can close the laptop entirely and just get a notification when the report's ready. Everything gathered during a research task has to fit somewhere. In the model's working memory, its context window, and that space is limited. Older models had a fairly small backpack. The newest ones can carry 1 million tokens at once. That's the difference between skimming a report and holding an entire library in view. A single real web page is stuffed with ads, menus, and boilerplate that has nothing to do with your question. So before a worker agent ever reports back, it filters its own findings, stripping the clutter down to just what's relevant. Only that small, clean note gets passed upward, which is the difference between an efficient system and one that drowns in its own noise. More thoroughness costs more compute, so most platforms let you choose. A faster setting runs around 80 searches for a couple of dollars. A maximum depth setting nearly doubles that search count for genuinely exhaustive coverage, at a proportionally higher cost. Depth, quite literally, has a price tag. Because these agents read raw pages from the open internet, a bad actor can hide an invisible instruction inside a page, hoping to hijack the agent when it reads it. This is a real, documented risk. It's called prompt injection, which is why safety training and system-level filters exist specifically to catch and block exactly this. In OpenAI's own published testing, this kind of attack succeeding dropped from around 4% to effectively 0 after those defenses were added. In practice, that protection is layered. These agents are typically read-only on your private data. They're blocked from constructing arbitrary outbound links that could leak information, and the underlying model itself is trained specifically to recognize and refuse a hijacked instruction. Learn language. Learn judgment. Plan the question. Split the work. Cross-check the answers. Cite the sources. That's the entire arc, from a model that only knew how to guess the next word, to a system that can go do a genuine day's worth of research while you do something else entirely. A search engine still finds you the shelf. Deep research is what happens when an AI actually sits down and reads it, all of it, and comes back with something worth trusting. That's what's happening in those few quiet minutes. If this video gave you a clearer picture of how LLMs actually work, please like it, share it with anyone studying AI, and subscribe to Draw the Logic for more visual deep dives every week. Thank you for watching.